So usually when we talk about a breakthrough in pure mathematics, we picture this um, very specific, deeply human scene. You know, the one.
Right, like a lone genius locked in an office.
Yeah, exactly. Staring at a chalkboard covered in chalk dust for a decade. It's like this romantic image of human obsession, just chipping away at the absolute limits of logic.
It's the classic archetype of scientific discovery. I mean, we imagine someone wrestling with an impossible puzzle until, well, eventually that flash of inspiration hits and the universe makes just a little more sense.
Right. But today, we are doing a deep dive into a scenario that completely shatters that image. On one side of this story, we have Donald Knuth.
Oh, yeah.
And if you are anywhere near the world of computer science, you definitely know that name. He is an 88-year-old titan, a Turing Award winner, the creator of the text typesetting system, and, the author of that legendary multi-volume series, The Art of Computer Programming.
He is, without exaggeration, the undisputed godfather of algorithms, a human mind at the absolute pinnacle of structural computational logic.
Yeah. And on the other side, we have Claude Opus 4.6, which is an artificial intelligence model that, at the time of this discovery, had been released exactly 3 weeks prior.
A literal infant, basically, taking on a problem crafted by an 88-year-old master.
Winning. I mean, the inciting incident for this deep dive is just incredible. Donald Knuth published an original paper on Stanford's website, and the very first 2 words of his academic paper are literally shock. Shock.
Because he was absolutely floored.
Exactly. This 3-week-old AI independently solved an open graph theory conjecture that he had been stuck on for weeks.
Which is, quite frankly, a paradigm-shifting moment.
Yeah.
Because pure math, like formal mathematical proof, has long been considered the ultimate impenetrable fortress of human cognition.
Right.
It's the one place where probabilistic text generators, the chatbots you might use to write an email, aren't supposed to succeed because they guess. And math doesn't allow guessing.
So our mission for this deep dive is to trace the exact 31-step methodological journey this AI took to get there. We are going to look at the prompt that made it possible, how the AI broke a decades-old assumption about generative models, and how this incident marks the precise moment these models cross the threshold from just being fancy calculators to true research collaborators.
In the wildest part of all this, we aren't just looking at an AI that magically spat out a correct answer.
No, not at all.
We're looking at a system that was forced to act exactly like a meticulous, highly disciplined graduate student.
Right. But to really appreciate why an absolute legend like Knuth was so shocked, we first have to understand the mind-bending scale of the problem the AI actually solved.
Yeah, we have to talk about the math.
And it's a problem involving what mathematicians call directed Hamiltonian cycles in a 3D toroidal space.
Which sounds terrifying.
Okay, yeah, stop right there. Just hearing the phrase directed Hamiltonian cycles in a 3D toroidal space makes my brain want to shut down. If I'm listening to this on my commute, I need a visual. We got to ground this.
Fair enough, fair enough. So let's imagine a massive three-dimensional city made entirely of one-way streets. It's a perfect grid.
Okay.
Let's say it is M blocks wide, M blocks deep, and M blocks high. And because it's a toroidal space, think of it like a 3D Pac-Man board.
Oh, right. So if you drive off the top edge of the city, you don't fall off.
Exactly. You instantly loop back to the bottom. If you drive off the east side, you pop out on the west side.
Okay, that's a perfect way to visualize it.
Yep.
So in this 3D Pac-Man city, every single intersection, which we can represent by coordinates I, J, and K, forces you to make a choice. Right?
Yes. You can only move forward in 3 specific directions. You can drive 1 block east, increasing your I coordinate. You can drive 1 block north, increasing your J coordinate. Or you can drive 1 block up, increasing your K coordinate.
Got it. So I'm standing at an intersection, and I have exactly 3 one-way roads leading out. What is the actual goal of the puzzle here?
The goal is to find 3 completely separate, continuous paths through this entire city. Each of those 3 paths has to visit every single intersection exactly once and then return seamlessly to its starting point.
Okay, that sounds hard.
And the catch is, the 3 paths can never, ever share the same street.
Oh, wow. Okay, so every intersection has 3 outgoing roads, and I have 3 paths to draw. That means I have to assign exactly 1 outgoing road to each path at every single intersection in the whole city.
Yes.
Mathematically, that just sounds like a combinatorial nightmare.
Nightmare is putting it mildly, because at every single vertex, you have 3 choices for how to route your cycles.
Right.
And since there are m-cubed total vertices in your city, the number of possible combinations you could try is 3 to the power of m cubed.
Okay, let's put some numbers to that so you can really feel the scale. Let's say we have a tiny city, Just 3 blocks wide, 3 blocks deep, 3 blocks high. So m equals 3.
Which is really small.
All right, the total number of intersections is 27. So the combinations are 3 to the power of 27, which is huge. But maybe if you have a massive supercomputer and you program it to aggressively prune out obvious dead ends, it could barely chew through that.
Maybe.
But what happens if you increase the grid to just m equals 5?
For m equals 5, you have 125 vertices. So the total combinations skyrocket to 3 to the power of 125.
Wait, 3 to the power of 125?
Yeah.
That is physically impossible for classical computers to brute force. Like, you could turn every atom in the known universe into a computer processor, let it run since the Big Bang, and you wouldn't even scratch the surface of that number.
Exactly. You can't just throw raw computing power at a number that big.
You can't calculate your way out. You have to find a hidden structural pattern, right? Like a mathematical law that governs the space, so you don't have to check every single combination.
Spot on. And this brings us to the core tension of the whole story.
Which is?
If brute force is physically impossible, and AI models are famously known for hallucinating.
Oh, right, for guessing blindly based on probability.
Exactly. So how on earth did a chatbot find a rigorous mathematical pattern? If you've ever tried to get an AI to do complex logic, you know it usually falls flat on its face. It just lies to you with extreme confidence.
Which is where human ingenuity enters the chat. Enter Philip Sappers. He's the human prompt engineer who brought this problem to Claude in the first place.
Right.
And his brilliance was that he didn't just paste the math problem into the chat box and say, solve this. He engineered a highly specific scientific constraint. He forced Claude to use a chronological lab notebook.
A markdown file called plan.md.
Yes. I read the system prompt he used, and it is brutally strict. He literally told Claude, after every run, immediately update this file, plan.md, before doing anything else. No exceptions. Do not start the next exploration until the previous one is documented here.
It's brilliant.
But why does this work? Like, why is forcing it to write a diary the secret sauce that cures hallucination?
Because it targets the fundamental architecture of how large language models work. LLMs naturally just want to generate the next most likely token. They want to rush to an answer.
Which is why they hallucinate. They just spit things out.
Exactly. By forcing the model to stop, open a separate file, articulate its hypothesis, document its dead ends, and analyze its failures before it's allowed to write the next line of code.
Sappers physically prevented the AI from skipping steps.
Yes. He turned a probabilistic text generator into a systematic explorer.
It's like the difference between asking someone to just shout out a random guess versus forcing them to sit down and write out their deductive reasoning for every single guess before they're allowed to speak.
Precisely. It forced logical iteration.
So because of this strict lab notebook, we don't have to guess how the AI solved it. We can actually open up plan.md and trace its thought process across 31 distinct steps.
And watching it systematically eliminate wrong approaches is fascinating.
So what did it try first?
Well, in step 1, Claude tried the obvious route. It attempted simple, linear, and quadratic mathematical variants. It basically looked for a simple algebraic function to determine the direction at each intersection.
Makes sense as a starting point.
Right. But it ran the code, and it failed. So the AI dutifully documented in its notebook, no linear or simple quadratic function works.
Okay, so it crosses algebra off the list. Then what?
In step 2, it tried exactly what we just said wouldn't work, brute force. It attempted a depth-first search mapping for the small m equals 3 grid.
Wait, slow down. What does a depth-first search actually look like in our 3D city analogy?
Imagine you're trying to find a path through the city, and you just start driving. You pick a road, then another, until you hit a literal dead end where you've trapped yourself.
Okay, I'm stuck. Now what?
A depth-first search means you then put the car in reverse, back up exactly 1 block, and try the other turn. If that fails, you back up again.
Ah, okay. So it's methodically checking every single route.
Yeah.
But because the city has 3 to the power of 27 possibilities, even at the smallest size, Claude realized it would be driving in circles, backing up and turning until the sun burned out.
Exactly. So Claude aborted the attempt. It documented in the notebook that the search space was simply too slow without aggressive pruning. It realized brute force was a dead end.
So it knows algebra is out and brute force is out. Where does it go for steps 3 through 14?
It shifts tactics entirely to dimensional reduction. Claude decided that 3D was just too chaotic, so it started analyzing 2D patterns to see if they could scale up. It tried what it called 2D serpentine analysis and modular Emery gray code.
Okay, modular Mary gray code is another one of those terms that sounds like an alien language to me. What is it actually trying to do there?
Think of it as trying to build a rigid, repeating pattern in 2 dimensions, like snaking back and forth across a flat floor that's the serpentine part, or using a binary flipping system, which is the gray code, to ensure you visit every square on a checkerboard.
Okay, that makes sense.
So Claude was trying to take those flat 2D checkerboard solutions and stack them up into a 3D cube, but it documented that these rigid patterns just couldn't be stitched together in 3D without the paths eventually crashing into each other.
You know what stands out to me here? How incredibly human this sequence feels. Like, the AI wasn't just throwing spaghetti at the wall.
No, not at all.
It was identifying entire classes of mathematical approaches, testing them, documenting their inherent flaws, and then crossing them off the list. It was genuinely learning from failure.
Which perfectly sets up the massive breakthrough in step 15. Because after failing with those 2D models, Claude realized it needed a radical shift in perspective to handle the 3D chaos.
The aha moment.
Yes. In step 15, Claude invents a concept it calls fiber decomposition. It defines a brand new variable, which it calls S, and it sets S equal to the sum of the coordinates. I plus j plus k modulo m.
Whoa, okay, hold on. You just threw an equation at me. My brain is still stuck driving around the 3D one-way city. If I'm standing at an intersection, what does this new variable S actually mean to me physically?
Okay, think about the physical movement in your city. If you take one step in any valid direction, whether you go east, north, or up, you are adding exactly 1 to your total coordinates, right?
Right, because I'm moving one block positively on the grid.
So Claude realized that if you group the intersections by the sum of their coordinates, every single step you take always pushes you from one sum to the exact next sum.
Oh.
It's like taking a chaotic loaf of bread and slicing it perfectly on a diagonal. Suddenly, the 3D city isn't a tangled web of cubes anymore. It's organized into neat, flat, diagonal layers.
I get called those layers fibers.
Exactly. It conceptually flattened the problem so that it only had to worry about how the roads mapped from one flat layer to the next.
That is genuinely brilliant. It took a 3D nightmare and turned it into an orderly sequence of 2D planes. But as I understand it, even with this brilliant setup, Claude falls into a trap right after this.
Yes, it does.
From steps 18 to 29, armed with these new flat layers, it tries to use computational heuristics, things like random local search, backtracking, and something called simulated annealing.
Yes, the heuristic trap.
I need another analogy here. What is simulated annealing?
Imagine you're trying to find the absolutely lowest, deepest valley in a massive mountain range, but you are completely blindfolded. Simulated annealing is an algorithm that mimics the cooling of metal.
Okay, so how does the cooling work?
When the algorithm is hot, you take massive, wild, random leaps around the mountain range. You're just bounding everywhere. But as time goes on and the algorithm cools down, your leaps get smaller and smaller until you're just taking tiny steps, eventually settling at the bottom of whatever valley you ended up in.
Okay, so it's a probabilistic guessing technique that slowly zeroes in on an answer. And the crazy thing is, in the notebook, it actually works. Claude uses this method and finds valid, perfect paths for the grids where m equals 3 and m equals 4. So why is this a trap?
Because finding a valley while blindfolded doesn't give you a map of the mountain range. Simulated annealing can find a specific needle in the haystack, but it doesn't tell you how the needle was forged.
Oh, I see.
It couldn't extract a general mathematical rule that would logically guarantee a solution for an m equals 5 city or an m equals 101 city.
And this leads to my absolute favorite quote from the entire 31-step journey. Claude realizes it's stuck, and it writes this in its own notebook. Simulated annealing can find solutions but cannot give a general construction. Need pure math.
Need pure math.
Yeah.
I mean, the profound nature of that self-reflection cannot be overstated.
It gives me chills.
We are talking about an artificial intelligence, a system built entirely on probabilistic computational guessing, recognizing the inherent limits of its own native paradigm. It voluntarily abandoned guessing to shift its cognitive framework entirely toward pure structural deduction.
That's wild. A machine built on guessing just admitted that guessing isn't good enough. So having abandoned heuristics, Claude finally cracks the code in step 31.
The final step.
It outputs a Python script utilizing what Knuth's paper later called the bump rule. Based on its notebook, Claude figured out that you can base your movement entirely on that diagonal layer we talked about, S, and by just checking a single coordinate, either I or J.
The rules it generated are astonishingly elegant. Depending on which diagonal slice you are on, you just check one coordinate and it tells you exactly which way to turn.
So simple.
Using this pure logic, the Python script yielded perfect Hamiltonian cycles, 3 separate paths, visiting every intersection, completely avoiding shared edges for odd numbers, all the way up to an m equals 101 grid.
But, as any mathematician will loudly remind you, a Python script that works 100 times in a row is just empirical verification. It is a very strong hunch. It's not a mathematical proof.
Right.
And this is where the architect, Donald Knuth, steps back into the story.
Exactly. An AI's working code is not a formal proof. You still need the human mind to explain the universal why. Knuth took Claude's programmatic output, reverse engineered the logic, and wrote the rigorous mathematical proof.
He showed the underlying truth.
He demonstrated exactly why these bumps in the code mathematically guarantee a continuous path without overlapping. He provided the formal human translation of the AI's empirical construction.
And Knuth didn't stop there. He analyzed the vastness of the mathematical space they had just conquered. He discovered that for the tiny 3x3x3 grid, there were 11,502 total possible Hamiltonian cycles.
Wow.
Out of those, there were 4,554 valid combinations. But Claude hadn't just stumbled onto a random one. Claude had navigated this massive combinatorial space to pinpoint one of exactly 760 unique, generalizable structural patterns that would scale up infinitely for any odd number.
It's like dropping someone into a galaxy with billions of stars, and they not only find a habitable planet on the first try, but they find the exact planetary alignment required to mathematically sustain life across the entire universe.
That is a perfect way to put it. But the story doesn't end there, because Claude solved this beautifully for odd grid sizes, right? Grids of 3, 5, 7, 9. But what about even sizes?
The grids of 4, 6, 8.
Yeah. Historically, even grids were unsolved, and mathematically they are far more chaotic because the symmetries break down differently. Claude actually got stuck trying to generalize the even numbers.
Which triggers the sequel to our story, the birth of a multi-agent ecosystem. Because once Knuth published his paper about Claude's success, the open source community swarmed the problem.
Yes, the baton gets passed. First, an anonymous user named Exosaja decided to combine two different models. They used GPT 5.4 and Claude 4.6 Sonnet to find an even simpler rule for the odd numbers.
Right.
It's listed as solution number 369 on Knuth's master list. An Exosaja solution completely ignores the I-coordinate entirely. It relies only on the diagonal layer S and the coordinate J, and uses what they called an identity permutation 012 almost everywhere.
Let's translate that. An identity permutation 012 basically means the simplest possible routing sequence. Road 0, then road 1, then road 2, repeating.
Just a simple loop.
Exactly. Exosaja's dual AI approach stripped Claude's original insight down to its absolute bare minimum, ignoring complex turns wherever possible.
And then the final fortress falls. The even M puzzle, the one Claude got stuck on, is fully conquered when a researcher named Hoboon Swan uses a different model, GPT 5.4 Pro.
This part is amazing.
Not only does this AI generate a decomposition for even grid sizes, testing it up to a staggering 8 billion intersections, but the AI independently generates a flawless 14-page formal mathematical proof.
A 14-page formal proof generated by the AI explaining the complex even number symmetries. It's incredible.
And just to tie a bow on the whole ecosystem, another researcher, Kim Morrison from the Lean community, which is a community focused on machine checkable math, used AI formal provers to verify Knuth's original proof in strict code.
Right.
And another analyst, Kesson Aquino-Michaels, published a full breakdown of how this multi-agent interaction actually worked.
This sequence of events raises an incredibly important point about the future of science. What we are seeing here is not AI replacing mathematicians. We are seeing a brand new paradigm of discovery. We can call it the human-AI symbiosis loop.
Break that loop down for us, because it seems to happen in very specific stages.
It happens in 4 distinct parts. First, you have the architect, in this case, Donald Knuth, the human who defines the boundary of the unknown and poses the right question.
The visionary.
Right. Second, you have the prompt Philip Stappers, the human who creates the strict methodological constraints, the lab notebook to keep the machine honest.
Curing the hallucination.
Yes. Third, you have the Explorer Claude, or GPT the machine, which navigates the impossible combinatorial explosions to identify hidden patterns that human brains just can't hold.
Because of the scale.
Exactly. And finally, you have the formalizer, the human mathematician, or tools like Lean, which cements that machine insight into rigorous, unassailable proof.
So if you are listening to this right now, why does this matter to you? The core revelation of this deep dive is that generative AI is no longer just a parlor trick. It's not just a fancy autocomplete that writes decent marketing copy.
Not anymore.
When bounded by strict scientific constraints, when forced to show its work in a lab notebook before it speaks, it can genuinely participate in the most guarded fortress of human cognition, pure logic and mathematical proof.
Think about Donald Knuth's reaction. This is an 88-year-old titan who has seen literally every single computing trend of the last half century come and go.
You've seen it all.
And he wrote, "What a joy it is to witness this dramatic advance in automatic deduction," and admitted he has to completely revise his opinions on generative AI. If someone with his legacy, his deep understanding of logic, is willing to fundamentally change his worldview based on this evidence, it suggests we all need to deeply recalibrate our expectations of what these tools can actually do.
Which brings us to a final lingering thought.
Yeah.
We see what happens when we unleash this human-AI symbiosis loop on the clean, abstract, perfect world of pure math.
Right.
But what happens when we point this exact same methodical lab notebook approach
Yeah.
at the messy physical sciences?
That is the frontier.
If a constrained AI can systematically navigate an impossible 3D combinatorial explosion with 3 to the power of 125 possibilities just to find a mathematical law, well, could it do the same thing with biology?
Exactly.
Could it sequence the next revolutionary protein to cure a disease? Could it sift through decades of quantum noise to discover a physical law of the universe that human minds simply aren't wired to conceptualize?
We've always had the diagnostic muddy waters, but now it seems we have a completely new kind of X-ray machine.
And it turns out all it took to turn a hallucinating chatbot into that X-ray machine was treating it like a meticulous grad student, sitting at a desk, writing in a notebook, one careful step at a time. Keep digging, keep questioning, and until next time, keep diving deep.